Okay, hello everybody. Today is our first lesson of random things that I am interested in. Um, so, uh, First, today we're going to be learning about the limit definition of integrals. So let's first cover what an integral is, just for your knowledge. Um, this it's not you don't need to know many other calculus topics to understand this, but um, just for the sake of this video, I'm just going to just give a quick rundown. Um, yeah. So if we make a graph, I want to make this green. Okay, let me erase this real quickly. Okay, if we make a graph, all right. Well, this is the x-axis and this is the y-axis. Okay. This is the x. And this is the y. Okay. Let's say we have some sort of polynomial. I don't know. Something like, I don't know. Oh, that was not good. I don't know why it needs so in response. Something like this. This is a really bad, almost looks like a sine wave, but like slanted. It's very bad representation, but this is what we're going to go with. All right. So, actually, you know what? Let me first start with the linear graph. I feel like that'll make more sense. Okay. So, okay. So let's say we have this graph, right? All right. This graph, okay, at I don't know 5. Okay, this graph is this graph is representing the rate of the rate of how many hot dogs I can eat over a certain amount of time. So we have hot dogs per, I don't know, hour. Okay, hot dogs per hour. Okay, let me just say, I don't know. This is hour. Yeah. Okay, hot dogs per hour. All right. So I have a constant rate of 5 hot dogs per hour over, over, let's say 4 hours. Okay, because as you can see here at 1, we have 5 hot dogs per hour. At 2, we still have 5 hot dogs per hour. At 3, we still have 5 hot dogs per hour. Well, then if you want to say, okay, well, am I dead yet? Because I'm eating a lot of hot dogs. So if we want to figure out how many hot dogs I've eaten over this certain amount of time, one can think, if we go away for a second and just think of it logically, right? Which is right, you have this, you're on a test, you say 5 hot dogs per hour, and then it has been 2 hours. Find the total hot dogs. Okay, you would be like, okay, well, this is pretty simple. We have our time, and we also have how many hot dogs per hour is eaten. So if we just multiply 2 times 5, because we are 2 hours, and in 1 hour 5 hot dogs are eaten, so that means it's 5 hot dogs and then another 5 hot dogs for 2 hours. So we have 5 times 2, which would be 10 hot dogs. Okay, but one might ask, One might ask, okay, well, how does this apply here? Well, it's very simple because as you can see, well, it has been 2 hours, okay? And at 2 hours, the 5 hot dogs per hour rate is constant. It has always been this way. So at 2 hours, we just fill this in. Hmm. This looks like a rectangle. What do we know about rectangles? We can find the area of rectangles, and that will give. And if you notice that 5 times 2, 5 times 2, in this word problem that we kind of made here is the same as finding the area of this rectangle. So then we can find that if we multiply x times y, we will get our total hot dogs. Now, someone will be like, oh, this is just simple, algebra. You could say algebra 1, even geometry, algebra 1, even 8, like, even you could say 7th grade math, or I don't know, elementary school. But, but little do you know, this is one of the bases of calculus. Because what if we have, let me erase all this. What if our rate of hot dogs that I'm eating is not constant? What if I, get sick a lot during the competition and I'm just like, I feel like I'm gonna throw up, so I'm like, oh, slowing down, and then, oh, I'm okay now, so I start eating more hot dogs, and then I slow down, and then I eat more, you know what I'm saying? That was a really bad explanation, but So now, I don't know, let's just make this, pink. I don't know, pink is a cool color. Oh, shoot. So in our new graph, we have, in our new graph, this is our new rate. Okay? This is our new rate. So I think a logical rate would be something like this here. Let me make this like red. Because I don't know, this kind of makes sense to me because in the beginning I have it, and then I'm really confident. I'm like, all right, and then I'm like, oh no, I ate way too much hot dogs fast, so I'm like slowing down. But I'm like, it's actually not getting that bad. I've taken my break, and and then no, it's too much. And this is my last bit. This is my last triumph. This is my last triumph right here. And then no, and then I pass out. Okay, that's how I see it. This is pretty logical in my case. We always need a logical example. If it's not, then everything doesn't make sense. So, anyways, back to the topic. So we'll be like, okay, well, this is, as we can see, this is not a linear graph. Okay, this is not y equals mx plus b. This is not linear. Okay, which is very, very, very important to understand this concept, because the whole point of calculus is that we're annualizing continuous change. This is all continuous change. At every given moment, there is a new rate at which I'm eating hot dogs. Okay, which is very different from just a constant rate of 5 hot dogs. This could be 5 hot dogs here. This is 3. This is 2.9. This is 2.8. You know what I'm saying? It's all changing. Now there might be times when it's the same. Let's say it's here, and let's say here and here it's the same. But as you can see, the distance at the time it took to here was not constant at all. So, and I'm saying this with I'm assuming whoever's watching it has a basic understanding of algebra, like kind of graphs. This is some sort of weird polynomial. I'm not gonna write this out, but that there is something to the power of something. X. So we know the x squared graph. It's like this and like this. that's x squared. All right, so you know something powered. So, all right, so if we want to further analyze this topic, okay, let's just do the same thing we did last time. So we have the starting as 5, and then we have 4 hours. Okay, we have our time, and then let me just say it's hours because I did that wrong last time. And then let me say we have our hot dogs per hour. Okay, so now we could do the same thing. Okay, so do part 1, 2 hours, 3 hours. Okay, so well, what do you notice here? If I'm at 2, oh, what the heck is that? That's not constant anymore. It's way off. This is not the same. This is, look, and if you shade it in, look, we're covering all this area. We're covering all of this. That shouldn't be that is not accurate at all. This is not telling us. This is a no-no. This is not telling us. This is not telling us how much hot dogs I've eaten in a period of 2 hours. Okay. Now, as you can say, sorry, no, but yeah. So, go back. Okay. So, a new solution, right? Why don't we just say, hypothetically, we have a scenario. So let's say, well, a great teacher offend you. Why don't we just put a bunch of, I think I can just draw this out. Where is it? Shapes, yeah. Why don't we just put a bunch of rectangles? Oh, whoa, that's weird. I'm very new to this software. I've never used this before. What the fuck? Why does it look like that? Oh shit, nope. Okay. Anyways, we're nope, I'm not doing this. Nope. Okay, you know what? We're drawing. Okay. So, well, you can ask great teacher India, why can't we just draw a bunch of rectangles under it? We can split these rectangles up, and we can make our own kind of weird shape that has all these different little sides, and find the area of each of these rectangles to have a much better idea, a much better approximation of how much hot dogs have eaten in 2 hours. Okay. So in this case, these are not even at all. Please don't hate me. This is very bad drawing, but I hope you guys get the idea. I'm drawing a bunch of rectangles under the graph. Well, what do you know here? Hold up. Wait, I want to do something. Well, guess what? Guess what? We can find the area of all these little rectangles. Okay? But isn't that tedious? Isn't that just annoying? You have to find every single rectangle, every single little interval. You know what I'm saying? That's just too much. Okay, we're close. We're much closer because now we only have all these little parts. We go brown. We only have all these parts that we need to get rid of. But it's just very tedious, and we still haven't gotten a good estimation yet. Now we could do this with trapezoids, but it'll be the same case. Because, it'll be the same case where it's not exact. Well, what if someone's analyzing to see if I'm cheating? What if the judge is like, hey, I think great teacher Fendiev is cheating. So what if he has to find the exact area under the graph to see how many hot dogs I've eaten over those 2 hours. So let's draw this again. Okay? Let's draw this again. Let's get blue. Oh shit. Oopsie daisy. Alright, yeah. Let's get blue. Oh shit. Okay, there we go. Okay, blue. All right. So let's kind of redraw that graph. What color am I going to choose? Ooh. Oh, I like this color. It's kind of like a lime green. Let's redraw it. Very inaccurate at this point, but you know, we're trying to just get the idea across. Okay, so we have our time. Okay. So probably should also draw this out too. Ooh, that's not accurate. Anyways, but you get the idea. So, well, okay. So we can't draw those little rectangles anymore because it's not going to work. So hypothetically, we would want the area under the graph to look something like this. Something we're shading in something under here. But that is continuous. Kind of looking, if you really think about it, you could think of it as like this, okay? The area under the graph kind of looks like this as a shape. If it was a shape, okay? They kind of like a shape. So, I think I can get the bucket. Oh, okay, nope, we're not doing that. You know why? Because this is messed up, yeah. Oopsies. Yeah, so, yep. So this is what the shape looks like. This is what our area under the graph kind of looks like. So, if you really think about it, you see here, hey, those are kind of like curvy, you know? That kind of looks like a circle. That kind of looks like a circle. Okay? And if we know it's from a circle, it has an infinite amount of sides. That's what makes it look so curvy. You know, I mean, that's what makes it look so curvy because you know it's just a bunch of little. It's just like because if I draw more rectangles, if I get a bunch of rectangles bunched together, you know. This would be really bad, but you get the idea. It's kind of a hypothetical idea of a circle, but then you keep doing more and more and more of these circles, I mean these rectangles, and you eventually get here. That's kind of what we're doing here, but under the graph. Because remember, we didn't want to do all those rectangles, and now we want to make it like this, where it's curved, continuous. Okay? That's what we were trying to do. So, well, great teacher Effendi, if you tell me all this crap, but how do we actually do that? Because it's all theory, but don't we want to actually use it? Because don't we want to actually see if I'm cheating or not? Because I know I ate a lot of hot dogs in 2 hours. I ate 10 hot dogs, and that's a lot of hot dogs, so I'm obviously cheating. So this is where we're going to bring in what we call the integral. Okay? Now, I'm going to start with what I like of the integral. What I like, not the introduction I've been taught in class, but more so my like what I like about it more, rather than how we were taught in the beginning. So let me find a cool color. Okay, yeah, this is a good color. Okay, so the area, okay, under the graph is equal to the limit. I'm assuming you already know what limit is, okay, because I'm not going to go through a whole unit of calculus. The area under the n to the limit n to infinity of the sum. Now, I'm also assuming you know what the sum is, summation is, sigma. Iterated by 1 to n, which is going to go to infinity, of the individual areas of each rectangle, which in this case would be this portion here is the individual area of the rectangles, okay? This is the individual area, so it's the sum of all of those infinite. This is a big part. We're making infinite rectangles, okay? infinite rectangles. So what does this mean exactly? What does this mean? Okay, well, what is change in x? Okay, change in x. So this looks really complicated, but we're gonna break this down. Okay, we're gonna break this down. Change in x. Change in x is equal to the second x value minus the first x value over n. Okay? Now, you'll be like, okay, well, okay, so let's just draw this on the graph real quick. The change in x from x equals 0 to 4 would be the final x value minus the initial x value. So that'll be 4 minus 0 equals 4 equals change in x. Okay, well, why do we have the n? Because, remember, we are having an infinite amount of infinity. So we need to have, so this is going to become 4 over infinity. That's obviously not possible, but we're going to have 4 over 2, 4 over 3, 4 over 4, 4 over 5, and so on. Because we're going to have an infinite amount of change of x's within the bounds of 0 to 4. Okay? So, now that we have that out of the way, let's continue on. By the way, it's like 12 a.m., but I'm going to keep doing this because this is cool. Alright, now, so we have the x, because you can think of this as a similar length times width equation with the area of a rectangle. This is the length, this is the length, or y, because, you know, as we can see in a rectangle, you can kind of see this as the y-axis, and this is the x-axis. Okay? Yeah, you see what I'm talking about? You see the resemblance? That's what's cool about it too. That's what's cool, because it's application of such simple math into something that so complex, we can just break it down to something so simple, which is what's really cool about this. So, okay. Continue on. So, now, what is this little baby? What is this baby? That's what my physics teacher called it. What is this baby? X sub k. X sub k. Let me write this in a new color. There we go. X sub k is equal to x sub k is equal to a plus change in x times k. Okay? Okay, change in x times k. Now, let's break this down. Let's break this down a bit. So, now, this is going to be the x values. This is going to be the x values that we need to input into f of x, okay, to reach that y value at that given point. So we have x sub k, and then we have what this specific y value is going to be. And then we have x sub k again, okay? But guess what? Change of x is different now. Change in x is different now. So this is a difference to x sub k, but we're still using this formula. So then we have another instantaneous y value, okay? And that's kind of going into the idea of derivatives and stuff, but I'm not going to go into that right now, because I'm assuming you already know what it is. So, we have that. And then we have a plus a. So, because think about it, we're starting at 1, which is a, and then we have x sub k, we would need to add this, add this, okay, add this 1 to get the total x value, okay, that would x sub k, okay, this is because this is what equals x sub k. So we just need to add these, okay, we need with this formula, and then we add this because we're gonna figure stuff out later once we solve this. But if we add these, okay, that's gonna get us our desired that's gonna get our desired x value. Sorry, it's gonna get our desired x value, which we can plug back in to the f function, which is y, and then get our y value. Okay. Oh, I hope I'm making myself clear. So now that is basically the basics of it. Okay. Now I am really tired, so I'm not going to solve it, but as a representation, again, we have our graph, and then we have all of these infinite, which is going to keep more and more, so many, just, you can't even think about it, how many rectangles are in this bounds, very specific, these bounds only, okay? You can't imagine how many are in here. And that's the whole point of this limit and this infinite sum of these infinite rectangles in this bounds, okay? And of course with this explanation more of the components, I hope you can understand that now. Now I'm probably gonna solve this in a later video because I'm super tired right now because this takes a long time to solve. So let me erase everything and just have a final conclusion. Okay? So, as y'all want to know, how many hot dogs can I actually eat in real life? Well, in reality, I can actually eat in 2 hours. I've tested this. In 2 hours, okay, 2 hours, I can eat 13 hot dogs. Now, that might sound insane, okay, right? I know, right? But I am 6'4" and I weigh 170 pounds. What does this mean? A shit ton of metabolism. Okay, shit ton of metabolism. Okay, metabolism. Okay, I am tall and scrawny. Well, I mean, I have a little bit of muscle and I have definitely a good amount of skinny fat. So this is kind of what I look like in real life. I mean, you guys have seen me, but not my body. This is kind of what I look like in real life, okay? I eat a lot of hot dogs, okay? So I can eat a lot of hot dogs, man. I can eat a lot of hot dogs, and it won't bother me. So 13 hot dogs, and I definitely threw up after that, but we're not going to go into that. So this is the conclusion. 13 hot dogs. That is how many I can eat in 2 hours. Okay? 13 hot dogs. Alright, I'm going to end the video now. Thank you all for watching. I hope I gave some good explanation, or maybe you learned something new, or you got exposed to something new, which is always the point of my videos. And the next video, I probably will be talking about how to solve this, or I might just skip it and just go on to some other math, or I don't know, maybe some sort of science related topic that interests me. Alright, have a good one, guys. See ya.